The largest release of radioactive materials in the last 46 years of U.S. history that was able to be measured and was not the result of a nuclear weapons test. The culprit in question was something fairly unexpected, originating from a natural and not human-caused disaster, specifically the enormous 1980 explosive eruption of Mount St. Helens. Yet, since the released radioactive material was not highly concentrated, the radiation was fairly harmless. Almost every rock contains very low concentrations of radioactive material, so if incredibly large volumes of it are ejected by an eruption, say 1.3 cubic kilometers worth of rock, it will also contain a large combination of radioactive materials throughout such a volume. Regardless, because volcanoes release radioactive compounds that release radiation, the measurements of such, particularly measurements of the element radon, can actually be used to both determine if volcanic unrest is ongoing and sometimes even help predict a likelihood of a volcanic eruption. For example, note how radon concentrations rapidly spike right before 3 of the Etna volcano's paroxysms in 2011. But, as you can tell from the amount of noise, this isn't a perfect, always conclusive measurement, just a helpful tool that should be taken in combination with multiple other factors when analyzing a volcano, especially during periods of volcanic unrest. This is why I am happy to partner with the highly relevant sponsor of today's video, RadiaCode. RadiaCode is a company which produces affordable yet highly effective smart and portable Geiger counters and spectrometers. These devices not only allow you to measure the amount of radiation in an area, but also visualize for yourself what isotopes are creating it via a free mobile app. This means that yes, you can even use RadiaCode devices that let you visualize the energy lines of incoming gamma rays and explore natural sources like Radon 222, the subject of this video, to help monitor levels of unrest at a given volcano. All you need to do is look for specific emission line peaks. While Radon 222 doesn't generally create much of a peak, its decay products of lead-214 and bismuth-214 do. Using the free mobile app available for Android, iOS, and desktops, all you have to do is look for these peaks for Radon 222 with your connected device, and these additional peaks for 2 of its decay products. Prices of various devices range from $229 to $599, which you can purchase on the official RadiaCode.com website with a 10% discount for the 102, 103, and 110 models by using the promo code GeologyHub. Simply visit the link shown on screen and mentioned in the video description, or even buy it through Amazon using this link that is also mentioned in the description below. Here is the RadiaCode 110 model I received, which works exactly as advertised. You can use it to monitor volcanoes, check a work site to see if it is safe, check surrounding areas while hiking and traveling, or even that one rock you found that you just had a hunch about was radioactive. However, you might be wondering why, of all of the radioactive elements, especially ones that are far more common, why are we measuring radon of all things to determine volcanic unrest? After all, the half-life of 3 of the 4 most common radioactive isotopes are over 1 billion years long, and these isotopes occur in the crust at concentrations in the very low parts per million range. Meanwhile, Radon 222, radon's longest-lived isotope, is around 10 trillion times less common. With a half-life of only 3.82 days for Radon 222, yes, days, across the entirety of Earth's crust there is never more than 11,080 kilograms of this element. For reference, the amount of gold in the Earth's crust, something that everyone knows is indeed quite rare, is 803.3 trillion kilograms. With that in mind, the key aspect that sets the element radon apart from every other element is that it not only occurs as a gas at room temperature, but this gas is the single heaviest elemental gas. And, at volcanoes, even very negligible amounts of radon gas present underground are frequently transported upwards by carbon dioxide, another gas all too common at degassing volcanoes. For reference, while air at sea level has a mass of 1,229 grams per cubic meter, carbon dioxide has a mass of 1,977 grams per cubic meter, and radon gas has a mass of 9,730 grams per cubic meter. Due to radon gas having such a high density, it is incredibly easy for ground and soil sensors to detect and measure it, especially because it is most likely to pull at elevated concentrations in natural low points surrounded by slightly higher topography. But what exactly creates the isotope radon-222 in the first place? Remember, essentially every rock contains negligible amounts of various radioactive elements, especially uranium and thorium, which occur in the parts per million range. Radon-222 occurs as a natural step on the decay chain of two of these elements' more common isotopes, specifically uranium-238 and thorium-230. So, where there is one isotope, there will eventually be concentrations of the other isotope. When magma rises through the crust, it brings with it small concentrations of these radioactive isotopes, especially radon, which is further concentrated by carbon dioxide gas. Also, that same magma movement can increase pore size in overlying rocks, giving radon gas an easier path to the surface, and even interact with and heat a region's water table, causing some of the radon it contains to rise to the surface. Areas of known faults, including caldera rims and hot springs, are more likely to see concentrations of radon gas increase during volcanic unrest involving magma. And now, here's a quick list of several volcanic eruptions where radon gas levels increased before an eruption commenced. Kurimsky in 1978, El Chichon in 1982, Popocatépetl in 1994, Cerro Negro in 1995, El Hierro in 2011, and Mount Etna also in 2011. As a final note, I want to remind everyone that the concentrations of radon gases that the vast majority of volcanoes emit and end up in nearby communities are generally too low to cause widespread health problems, although some exceptions do exist. I would now like to thank my new patron Caroline Cheshanovsky for supporting my work and want to once again thank RadiaCode for sponsoring this video.